All right, let's do another vector math practice problem. So in this problem, we've got three forces that are acting on a stone, and those forces are called A, B, and C. We want to find the magnitude and direction of a fourth force such that the stone is in equilibrium. And so I've already drawn a picture here for what this problem is supposed to look like. We've got the three forces, A, B, and C. They're making some angles between themselves and the x and y axes. Actually, let me label this for C. This is 53 degrees. Oops, 53 degrees. And so with this, we can start kind of visualizing how this physically manifesting. So at least three forces pulling on the stone. Just the way, imagine kind of looking down on three people pulling on something with ropes, right? They're all trying to pull in these directions, A, B, and C. And you can imagine that with these three forces, the stone's probably going to move off in some direction, right? Force A is pulling on it pretty hard off to the right there. Force B is kind of pulling it up a lot. Force C is kind of weak, pulling off to the side. The stone's probably going to drift off in this direction or something. And so the idea here, what the problem's asking us to do, is imagine that there's this fourth force, which we'll call that force D. This fourth force, such that vector D causes this stone to be in equilibrium. Equilibrium means that if we were to add this fourth force vector D plus the three other forces that are already there, vector A, vector B, and vector C, if it's in equilibrium, then they have to all equal 0. Right? Equilibrium means that the resultant force, the result of all the forces added together, is 0. And so in this case, we can kind of imagine, where should this vector D, this fourth force, be? We can just kind of make a guess, and my guess is it's going to go off in this direction or something like that. Just because it needs to cancel out the action that all the three other forces, A, B, and C, are applying. That's just a guess. I'm going to give us a frame of reference here. But we can dive into actually solving this thing. And the way that we want to solve this, remember, we're looking for the magnitude and direction of this fourth force, force D. So I can start solving for that. I can say that the force D is just equal to, and rearrange this equation, minus force A plus force B plus force C. Rearranging that equation there. So to actually solve this, I just need to look at each of these forces A, B, and C and break them apart into we call their components. Each of these forces have an X component, a side-to-side piece of them, and a vertical component, a Y piece, up and down. And so I'll take this one at a time here. I'll get vector A first. The way that we break this any vector into components, we start with the horizontal piece, the X component, and that's equal to always the magnitude of the force, which in vector A's case is 100 newtons, as you can see in the image there. 100 newtons times the trigonometric function that isolates the horizontal piece of the vector. So in this case, that's going to be cosine of the angle that they give us here is 30 degrees. So cosine of 30 degrees isolates that horizontal component. And if you aren't sure about the trigonometry part, we'll have a separate video on that. Just take my word for it if you're sure about it, or if you are sure to treat this as practice. But I wanted to note that this is the horizontal component, the X component, by giving it this I hat designation there. And so to this, so we've got now we did the horizontal component of vector A. Now I want to look at the vertical component, which is very similar. It's going to be the same idea, the magnitude of the force times, in this case, it's going to be sine of 30 degrees in the J hat direction. So I hat side to side, J hat up and down. And what we've done here is we've separated this vector A, which is 100 newtons in magnitude just on its own, but we've split this up now into its horizontal piece and its vertical piece. And we're going to do the same thing with vector B. Vector B, same idea. We get the magnitude of the force, so that's 80 newtons, times the trigonometric function that isolates the horizontal component. So for vector B over on our picture here, we got a horizontal piece like that, and a vertical piece like this. And given how they've described this angle right here, this 30 degrees, the horizontal component of vector B is going to be sine of that angle, which is also 30 degrees, the I hat direction, plus, again, the magnitude, 80 newtons, times cosine, 30 degrees, j hat direction. This is a good opportunity to prove to yourself. If you're unsure why in vector A we did cosine of 30 for the I hat component, the horizontal piece, and in vector B we use sine. So those two things are different. It takes some time aside to prove that to yourself just based on our image here. Why is that the case? It's some good practice. But we'll do the last thing, last step here with vector C. And actually, I just noticed something that I neglected. For vector B here, we have to be a little bit careful. The horizontal piece of vector B, you can see vector B is going off to the left, meaning that the horizontal piece is pointed in the negative x direction. So I got to be a little bit careful here. This the I hat component has to have this negative sign. Actually, we'll do it in red. We got to be extra careful about it right there. That's a negative sign that we need for the x component of vector B. Similar thing for vector C. We see vector C is going off to the left too, so it's got to have a minus sign in front. Then otherwise it's similar idea, the magnitude, which is 40 newtons, times the function that isolates the horizontal component, which is going to be cosine of the angle that they give us, 53 degrees, the I hat direction. And then for vector C, it's also pointed downwards instead of for the vertical component, unlike vectors A and B, which their vertical component is pointing up. So we've got to have a minus sign here as well. 40 newtons times sine of 53 degrees in the j hat direction. So everything we have here for vectors A, B, and C, we can combine those together with a calculator. We can multiply 100 newtons times cosine of 30. We can get that into a number. And we can boil this all down and put this into our equation here for vector D. I'm going to do that kind of off to the side, but just take my word for it here. The result that we get is vector D is equal to, I'm going to keep this, the I hat, I'm going to combine the I hat components, the horizontal pieces, and the j hat components, the vertical pieces. And I get the result that vector D is equal to negative 22.3 newtons in the I hat direction, minus 87.2 newtons in the j hat direction. So that's all well and good. That's our vector components for vector D. So we're really close to what we want to actually solve for. The problem asks us for the magnitude and direction, though, of vector D. I'm going to do that here. The magnitude of vector D, and the way that we solve this is the way that we solve the magnitude of any vector, which is we take the square root of the x components, which is, in this case, minus 22.3 newtons, and square it, and add that to the square of the vertical components, which is 87.2 newtons squared. All that under the square root. And so here we get the magnitude of vector D is equal to, we plug that into our calculator, and it comes out to 90.2 newtons. So just like how vector A had a magnitude of 100 newtons and vector B was 80 newtons, vector C is 40 newtons, vector D 90.2 newtons. A little bit stronger than force B, a little bit weaker than force A. But that's the first part of our answer there. To get the direction that vector D is pointing in, I'm going to do the following. I'm going to say that I know that the tangent of any angle is equal to the opposite side of some right triangle over the adjacent, so the ratio between these two things. And so in the case of vector D, the way that I can think of this is just based on how I've drawn it in our image here, or I draw it off to the side. This got some angle here that we don't know, and we've got a corresponding adjacent side, opposite side, adjacent and opposite. And so I can solve this. I can move this around and say that theta, right? We're trying to find the angle, trying to find the direction here. So theta is equal to the inverse tangent. Oops. The inverse tangent of the ratio between the opposite side and the adjacent side of this right triangle, which in the case of vector D, we have that information. We know that the vertical component, the opposite side here, is negative 87.2 newtons. And the adjacent side is the x component, negative 22.3. So we actually have those numbers. We can plug that in. We can do this calculation in our calculator, inverse tangent. When we get an angle, if I, the value I get out of this is 75.5 degrees, which on its face, we get a number, so that seems good. We're like on the right track here, obviously. But we want to be a little bit careful, because just looking back at our picture here, if I draw an angle of 75.5 degrees, that angle's always, like, we solve it like this, angles start from the x-axis. An angle of 75.5 degrees comes out to like right here, 75.5 degrees. And that seems kind of weird, right? Like if we think about this problem, if vector D pointed off in that direction, it's got 90.2 newtons, vector D. That seems a little strange, right? Because we wanted to find it such that vector D causes equilibrium. We want this to be, including vector D, we want it to then cancel out all the forces. And so this seems kind of not right? If vector D went off in that direction, probably the total pull on this weight is going to be off in that direction as well. So this is like almost right, not quite though. There's a little bit of a trick where when we do inverse tangent, there's actually two results possible that come out of this. It's the value that we just found, the 75.5 degrees, and that same value, but added to it 180 degrees. There's two possible answers here. So the other answer could be this plus 180 or so. It's like something like 256 degrees, maybe 256.5. And what that means visually, if we look at our piece here, instead of vector D going off in that direction, instead we're saying something like this, like vector D is very similar to vector C. It's like going off like that. And that makes much more sense. I mean, just physically, put this weight in equilibrium. We're adding this fourth force to cancel out all the others. That makes a little bit more sense, at least it does to me. And so that is, in fact, our correct answer. 256 degrees, which is the angle that is made from the positive x-axis all the way around right here. 256 degrees for our vector D. So we have our two pieces of our answer here. We've got magnitude of the force, which is 90.2 newtons. We found that by adding up all the components, the x and y components of all the other forces. and then calculating the magnitude. And then the angle that that force is pointed in is 256 degrees, because we got two answers out of our inverse tangent, one of which didn't really make physical sense, but that's okay. That just helps us decide which one of these answers is the correct one. 256 degrees is our answer. And that's this problem. Pretty straightforward. But if you have any questions, be sure to leave a comment. We'll go through some more questions or some more problems in the future, and we'll stop back on this if there's any need for review. Great. Thanks again, and yeah, tune back in for some more practice problems.